So let me please present our paper, Cross-Domain Reconfigurable GAN with Fuzzy Components for Anomaly Detection. My name is Alexander Stryuk. I'm a PhD student, Petro Могила, Black Sea National University, Ukraine. Table of contents, introduction, background of GANs and related work, GANs in anomaly detection, proposed anomaly detection architecture, area of potential applications, challenges and drawbacks, further research directions, and conclusion. So anomaly detection remains critical in various domains, including cybersecurity and healthcare monitoring. Traditional approaches often rely on low-level machine learning and statistical methods, which may struggle to capture complex, multidimensional data patterns and adapt to evolving anomalies. In recent years, generative adversarial networks, GANs, have demonstrated promising potential for anomaly detection due to their ability to learn the underlying data distribution. This presentation reviews a simple anomaly detection system prototype which leverages a GAN-based model integrated with fuzzy logic components. We explore integrating the GAN architecture with auxiliary components to deploy the anomaly detection system and enhance its performance and robustness. This approach endeavors to explore the practical potential of GAN-based models in anomaly detection and paves the way for future research in this rapidly evolving domain. Anomaly detection is a fundamental task that plays a highly important role in various applications in main scientific, technological, and business domains, including cybersecurity, finance, healthcare, natural sciences, astronomy, the Internet of Things, and marketing. The ability to identify rare and abnormal events or patterns in large data sets is vital for ensuring system integrity, detecting fraud, diagnosing diseases, and maintaining overall operational efficiency. Traditional methods for anomaly detection, such as statistical techniques and rule-based systems, have been widely employed, but however, these methods often struggle to handle complex data distributions and adapt to evolving anomaly patterns, leading to limited detection accuracy and high false positive rates. To overcome the limitations of traditional anomaly detection methods, there is a growing need for more advanced techniques that can effectively capture intricate data patterns and provide robust anomaly detection capabilities. Generative adversarial networks have emerged as a promising approach in this regard. Background of GANs. GANs are a class of deep learning networks that consist of two components, a generator network and a discriminator network. The generator aims to generate synthetic samples that mimic the real data distribution, while the discriminator learns to distinguish between real and generated samples. Through an adversarial training process, GANs learn to capture the underlying data distribution and generate high-quality samples. The potential of GANs in anomaly detection stems from their ability to learn complex data distributions and generate realistic samples. By training GANs on normal, real data, they can learn the underlying hidden, unobvious patterns and generate synthetic examples that represent the normal behavior of the system. Consequently, when presented with unusual or novel data, GAN-based models can identify deviations from the learned distribution, flagging potential anomalies. The following is the flowchart of conventional GAN that was presented by the author of the architecture, Ian Goodfellow, in 2014. The following is the mathematical depiction of the Minimax two-player game that is used in GANs. I mean, in the conventional GANs as the objective function. Related work. The following are various science and technology domains where GANs have been successfully utilized: image and video generation, healthcare and medical imaging, natural language processing, NLP, drug discovery, robotics and autonomous systems, data privacy and security. GANs in anomaly detection. GANs have also found applications in anomaly detection. The basic idea of this approach is to leverage the generative capability of GANs to learn the underlying distribution of the normal data, including both local and global patterns, and then use this model to identify anomalies. This can be achieved by training the GAN on a dataset composed solely of normal instances. Once the training is complete, the generator can be used to generate synthetic data, and the discriminator can evaluate the dissimilarity between the generated samples and the real data. Instances that the discriminator classifies as significantly different from the real data are considered anomalies. In anomaly detection, the goal is to detect data points, instances, or events that deviate significantly from the expected or normal behavior. Traditional anomaly detection methods often rely on statistical or low-level machine learning techniques such as z-score, box plot, clustering, classification, Gaussian mixture models, or distance-based approaches to identify deviations from the norm. These methods struggle when dealing with complex and high-dimensional data, as well as detecting subtle anomalies. GAN-based anomaly detection methods also may face challenges, such as the difficulty of accurately modeling the normal data distribution, the potential for false positives or false negatives, and the need for careful training and fine-tuning to achieve optimal results. Nonetheless, GANs offer a promising approach for anomaly detection in various domains where they can complement or even outperform traditional techniques. Proposed anomaly detection architecture. The main objective of our research was to build an anomaly detection model based on the conventional GAN architecture, keeping it as simple as possible both in terms of computation and architecture using PyTorch with Kaggle environment. We designed a model comprising two basic components, the generator and the discriminator. The generator's purpose is to learn how to generate data similar to the trained dataset, while the discriminator aims to distinguish between real and generated data following the standard GAN framework. For training, we utilized the MNIST dataset, a straightforward collection of graphical data. MNIST consists of 28 by 28 pixel images of handwritten digits from 0 to 9, and the sample of the dataset can be seen on figure 2. For the purpose of anomaly detection, we considered images of digit 1 as normal data and the rest of the digits as anomalies. We preprocessed the data by splitting it into sets. Training set consisted only of images with the digit 1. Normal data test set included images of all digits, both normal and anomalous, and a small fraction for the validation set while we trained the model to assess its performance. Generator, a neural network with 3 fully connected layers, including the input and output layers. The input layer has 100 units representing random noise, and the output layer has 784 units corresponding to the flattened 28 by 28 pixel images, all from the MNIST data. The generator uses the ReLU activation function for the hidden layers and the 10H activation function for the output layer. Discriminator, a neural network with 3 fully connected layers as well, including the input and output layers. The input layer has 784 units, 28 by 28, corresponding to the flattened images, and the output layer has only 1 unit, representing the probability that the input image is real or not. The discriminator uses the ReLU activation function for the hidden layers and the sigmoid or logistic activation function for the output layer, because it's actually the binary classification task at the end. We trained the model in an adversarial approach. The discriminator was trained to distinguish between real and generated images. It was updated using binary cross-entropy loss, where real images were labeled as 1 and generated images as 0. The generator was trained to fool the discriminator by generating images that the discriminator would classify as real. The generator was updated using binary cross-entropy loss as well, where generated images were labeled as 1, trying to make the discriminator believe they are real. We also applied the Adam optimization algorithm, setting up the following parameters: 0.002 for 0002 for both generators and discriminators learning rates, and 0.5 and 0.999 for betas. We implemented anomaly detection using the following approach. After training, we used the generator to generate new images and computed the mean absolute error between the generated and real images, which included images of all digits from 0 to 9, to measure the quality of the generated images. The MAE is calculated as the mean square error between corresponding pixels of the images. We use this loss as an anomaly score with higher scores indicating a higher likelihood of being an anomaly. We evaluated the model using the test set and computed the area under the receiver operating characteristic curve and the classification report to assess the model's performance in detecting anomalies. The model achieved a UC of 0.95, indicating that it can effectively distinguish between normal and anomalous images. The classification report showed that the model could correctly identify most anomalies, although the precision for the anomalous class was relatively low due to the imbalance in the test set, because test set contained more abnormalous anomaly data than training set. For better estimation, we also used the SK fuzzy library to implement the fuzzy logic component in our anomaly detection model. The SK fuzzy library provides the tools to create and manipulate fuzzy membership functions. We defined 3 fuzzy sets for the anomaly scores: low, medium, and high. These sets are represented by triangular membership functions. The parameters of this function are the universe of these scores, X score, and the 3 points that define the triangle. For example, for low set, the triangle is defined by the points 0, 0, 0.3, which means the membership function starts at 0, peaks at 0, and ends at 0.3. We converted the crisp anomaly scores into fuzzy scores using the fuzzinterp membership function. This function calculates the degree of membership of a given value in a fuzzy set. We applied this function to each anomaly score to get its degree of membership in the low, medium, and high sets. We aggregated the fuzzy scores using the average method to get a single fuzzy score for the entire dataset. This score represents the overall level of anomalies in the dataset. We also converted the fuzzy score back into a crisp value using the centroid method. This method calculates the center of mass of the fuzzy scores membership function. The result is a single crisp value that represents the overall level of anomalies in the dataset, figure 4. The purpose of adding the fuzzy logic component to anomaly detection model is to provide a more flexible and interpretable assessment of the anomalies. Area of potential applications. In the burgeoning landscape of data-driven technologies, the anomaly detection system built upon GANs combined with fuzzy logic components exhibits the potential for wide applicability across various domains. The model's capacity for unsupervised learning renders it particularly beneficial for scenarios where labeled data is scarce or costly to obtain. Within the industrial setting, it could revolutionize quality control mechanisms by pinpointing defective items and predictive maintenance by identifying machinery on the verge of failure. Furthermore, the financial sector could leverage such models for advanced fraud detection, notably in credit scoring and financial transactions. The healthcare industry can also get benefits. For instance, its application in medical imaging could facilitate the identification of anomalies in radiological images such as X-rays and MRIs. Additionally, real-time patient monitoring could be enhanced to detect abnormal vital signs, thereby preventing critical health events. Equally, in the realm of cybersecurity, the model could function as an intrusion detection system capable of identifying unusual network behavior and potential malware attacks. Challenges and drawbacks. While this type of model has shown promise in anomaly detection tasks, it can also encounter several challenges and drawbacks that need to be thoroughly considered. The following are some of the main challenges: complex training and tuning, limited anomaly diversity, data imbalance, scalability, sensitivity to noise, outliers, and unseen anomalies. The model's ability to detect novel or previously unseen anomalies can be limited, requiring additional techniques for detecting such anomalies. We're going to strive to address these limitations through further research, model enhancements, and tailored adaptations to specific applications. Our primary objective is to develop a fully operational model, building on our preliminary simple design that's well suited for targeted real-world applications. Below are key research directions for advancing in our endeavor. First, exploring novel training techniques tailored for GAN-based anomaly detection models with a fuzzy logic component to enhance stability, convergence, and performance. Investigation of alternative GAN architectures, for instance, DC GAN, W GAN, style GAN, etc. Loss functions, regularization methods, and optimization algorithms. Investigation of the combination of GANs with other deep neural network models or architectures, such as variational autoencoders or self-attention mechanisms. Third, in terms of the imbalanced dataset problem, we might also consider using techniques specifically designed for imbalanced data, such as oversampling the minority class, undersampling the majority class, or using a different evaluation metric that takes class imbalance into account. Conclusions. We've designed a preliminary model for an anomaly detection system integrating a GAN with elements of fuzzy logic. We have discussed the background of GANs and their application in anomaly detection, as well as the specific architecture. We have also highlighted key research directions for advancing GAN-based anomaly detection. While our work represents an early phase of the research, in summary, such GAN-based anomaly detection systems, augmented with fuzzy logic, offer a prospective, adaptable framework capable of handling the uncertainties and ambiguities inherent in real-world data. Its versatile nature makes it a good candidate for deployment in a myriad of sectors. We intend to improve the model further using other real-world datasets, validate its performance, and conduct comparative studies to focus our future endeavors on improvement anomaly detection methods. Thank you very much for your attention.
Thank you, Alexander, for your presentation. Now we have time for question. Colleagues, please. Okay, Evgeny, please go ahead.
Good day. Can you explain me what you call anomalies?
Sir, can you please repeat?
What do you call anomalies in your research?
Okay, thank you very much. As for anomalies, we consider anomalies as any abnormalities, unobvious, non-standard data that doesn't fit the data distribution that the model was learned on. So any data that the model can consider as unseen or unknown for its knowledge base.
And this anomalies is specific for each task, or it can be in every task. It can be same anomalies.
For sure, the anomalies vary from task to task. If it's, for instance, cybersecurity, it would be one set of anomalies and with their own features and peculiarities. If it's medical or healthcare tasks, the anomalies will be different. But in terms of perspective of this approach, we're thinking of improving the generalization of models. So the main aim here is to develop the model that can be generalized to all of the anomalies, no matter from what domain, what roots or what domain they are from.
Okay, thank you for your answers.
Thank you.
Any other comments, questions, colleagues? Alexander, I have some very simple question for you. GAN system is being widely used for anomaly detection, so it's known fact. You develop some kind of new architecture, some kind of optimized. Thinking about performance-wise question, could you say your system is more like have some kind of more improved performance, some kind of speeds, whatever. So could you tell me, elaborate on the topics, your performance of your system or your architecture is much better than, let's say, existing GAN model for anomaly detection? Because again, it's like very wide topic you're dealing with. You improve something. Could you elaborate on that?
Thank you for the question. The main majority of GAN-based anomaly detection systems that I found are computational demanding, and almost all of them have a super sophisticated architecture. The main aim for this research was to try to build, in terms of proof of concept, the simplest possible model that can do the same, or at least partially, in terms of partial precision and quality, as these highly sophisticated, overloaded with layers and neurons models. So in terms of computationally wise, we believe that this approach and this prototype can outperform this highly overloaded with sophisticated architecture models. So this is our main goal, to improve this model further, increase its precision, because the precision was not that good, but the accuracy in identifying anomalies was quite good, since it's 0.95.
Oh, okay. And my next question would be related to vulnerability of your cyber vulnerabilities of your system itself. So it means, my question from cyber perspective, is your model cyber, let's say, could be have some kind of vulnerabilities related to cybersecurity? Because I guess you need to you have to train your model to provide some kind of data as an input. You can how you can, are there any issue related to the cybersecurity of the model itself?
Yeah, I guess definitely it's a separate big topic for a separate research. I mean, the possibility to exploit our model. This is really interesting question, and it requires additional research. But in terms of application cybersecurity of such models, for instance, we have this publicly available data set, which is called MalVis, and it represents the malware collection of different types of families of malware, represented, I mean, their binary files are represented as image. And this approach, when we transfer such types of data, like malware binaries, into image representation, we can, this is where GANs are at the top of performance, because they are really stable in terms of processing the graphical data. So we can take this particular task, I mean, graphical visual representations of malware, and we can train the GAN models to first to generate malware in graphic, and then we can translate it into real binary files. I actually don't know if it's possible, but I assume that it is possible. And then the second one, we can use such model with the same type of architecture to train it to identify malware or anomaly malware by examining such graphical representations of real malware binaries. I guess we can consider it even in this regard. And also GANs are extensively used in the cybersecurity domain in the field of password generation, because there was this application which is called GAN or something like that, and there was a paper published on this topic that it can actually GAN models can actually generate real life passwords that can be added to this password database that is using to in the brute force attack tools, something like that. But I didn't go that deep in this particular direction.
Yeah, it's a really good point to mention, because as you're targeting some kind of medical application, you're going to suggest to use your system for the medical domain. Just not to forget about security,
Yes,
cyber
of course.
security system itself, because it would be main question from the potential clients: is it protected?
Yes, for sure.
Yeah, not to forget. Okay, thanks again.
Thank you
Alexander, for your presentation. Let me invite next speaker.